Hey everybody, here are the notes for homework number 16, part 2, which is covering optimization, which is really just word problems where we kind of have to find a maximum or minimum value, and they kind of all have the same sort of procedure. So let's look at this first problem. If two numbers add up to 12, what is the maximum value of their product? So typically with these questions, you have a constraint and then a function or thing that you want to optimize. So in this case, our constraint is the fact that we have to have two numbers that add up to 12. We can call them whatever we want, typically x and y. So we're constrained by the fact that x plus y has to be 12. And then we want to optimize the product of those two numbers. So the product, which is going to be x times y. Notice that while the constraint is an equation that's equal to a number, the thing we want to optimize is just some expression that doesn't have an actual value yet. Our job is to find the biggest it can be. So just kind of, for example, some values for x and y that might work, right? If x is 1 and y is 11, the product would be 1 times 11. And if x was 2 and y was 10, the product would be 2 times 10, which is 20. If x was 3 and y was 9, 3 times 9 is 27. 4 and 8, 32, et cetera, et cetera, et cetera. So if you really did this to exhaustion, you might be able to find the numbers just by doing it. Although, depending on the values, you might not actually get there. So it's always safer to do it the following way. We're going to typically, after we do this, then our job is to rewrite the thing that we want to optimize as a function of one variable. So what that usually means is taking the constraint, x plus y equal to 12, and isolate one variable. It doesn't really matter which one. Pick whichever one you like. I'm going to isolate y. I'm saying that y equals 12 minus x. And now we're going to plug in y equals 12 minus x for y in our optimization equation. P equals x times y. So what we're going to do is we're going to say that now our product is x times 12 minus x, which is just our x times y. So now we can write this as a function p of x equals x times 12 minus x. Now I'll point out, if we multiply this out, we can see that our product or function of x is 12x minus x squared, or if you prefer, p of x is negative x squared plus 12x. And that's a parabola that opens downwards. And we know how to find the maximum value of a parabola that opens downwards. We have to find the y-coordinate of the vertex. I'll point out that here, my a is -1, my b is 12, and my c is 0. So I want to find the x-coordinate of the vertex. It's going to be negative b over 2 times a, which is -12 over 2 times -1, which is positive 6. So the x-coordinate of my vertex is 6. The function coordinate, or the y-coordinate, or the output, if I plug 6 back into my function here, p of 6 is going to be, I like plugging it in here, 6 times 12 minus 6, which is 6 times 6, which is 36. So a couple things here. The maximum value is 36. The x and y numbers that give us that are x equal to 6, and y isn't 36. Y would also be 12 minus 6, so y would be 6 as well. So be careful here. The y value isn't the y-coordinate necessarily of the parabola. It's the other thing you would find, right? I found x equal to 6 right here, and then my corresponding y value is also y equal to 6. So 6 plus 6 is 12, and 6 times 6 is the maximum value you can get when two numbers add up to 12. I should say the maximum product you can get. So I would write down here that the maximum value of the product is 36. The question could also have been phrased as find the two numbers that give you the maximum product, and then the two numbers would be x equal to 6 and y equal to 6. Now, I suppose I should put down the little code for the homework assignment. So let's say, let's see, this is homework number 16. Let's say sweet 16. Sweet in uppercase, sorry, S in uppercase, everything else in lowercase. So uppercase S, WEET 16. That's for homework number 16. Let's see here. So, second question. A farmer has 1,200 feet of fence to build a rectangular corral, but one side will be adjacent to a river and will not need fencing. So like this, here's my river, here's my corral, it's got fencing here, here, and here. What dimensions will give a maximum area? So I'll point out that when you have a situation like this and you don't know the side lengths, it's good to draw a picture and we should label them with variables. I've called this side X and this side X because in the rectangle, those two sides have to have the same length, so we shouldn't use more variables than we need to. And again, we have two things going on here. We have a constraint. Here we are limited by the fact that we only have 1,200 feet of fencing. So we know that this side plus this side plus this side should add up to 1,200. I suppose it could add up to less, but if we're trying to make the biggest enclosure possible, we want to use all of our fencing. So then I'm going to simplify this and say y plus 2x equals 1,200. And then we also have the thing we're trying to optimize. In this case, we're asking what dimensions, so what values of x and y will give a maximum area. So we're trying to maximize the area of the enclosure, which is the area of a rectangle, which is base times height, or in this case, x times y. And just like in the last problem, the thing that we're trying to optimize has two different variables in it. We'd like it to only have one, because then we can write it as a parabola typically, and then see where the vertex is. So just like before, we're going to take this constraint, we're going to say, okay, well, let's isolate y, or really isolate either one. But again, here it's especially better to choose y, because if I tried to isolate x, I'd have to divide both sides by 2, and I'd rather not. If I isolate y, I'm going to get y equal to 1,200 minus 2x. Then we're going to plug that back into the thing we want to maximize, and area equal to x times y is now going to become area equal to x times 1,200 minus 2x. Sorry, you can't see that, apologies. We're going to multiply this out, so area is equal to 1,200x minus 2x squared, or preferably negative 2x squared plus 1,200x. We're again going to find the vertex of the parabola. So I'll point out that if you graph this thing, let's find the vertex first. So the x coordinate is going to be negative b over 2 times a. Negative 1,200 divided by negative 4 is positive 300. And if you plug this through here back into here, you're going to find the maximum area. So I'll point out that if you're going to graph this parabola, you have the x-axis and the area axis essentially, and it looks kind of like this. Where, oops, sorry, apologies, I keep reading the last screen here. So like, here's my vertex where the x coordinate is 300, and the area would be, well, if x is 300, then this side is 300, this side is 300, and this side is the leftovers, which is 600. So the area would be 300 times 600, which is something like 180,000, I think. But that's not what they're asking for, right? They didn't ask for what the maximum area was. The question was, what dimensions will give a maximum area? So we found that x needed to be 300 feet. And then we know that y is equal to 1,200 minus 2 times x. So y is going to equal 1,200 minus 2 times 300, which we already knew was going to be 600. Y is equal to 600 feet. Those dimensions add up to 1,200, right? Because you have 300 plus 600 plus 300. And those dimensions give you a maximum area, because any other value of x would give you a lower point on the parabola. So these two dimensions maximize the area enclosed. And then even though it wasn't asked, I'll point out the area would be, or is, 300 times 600 square feet. But again, you really only have to answer the question that's being asked. In this case, they didn't ask you what the area was, they asked you what the dimensions were. And it's really important to pay attention to what is actually being asked. One more question. So this one is find the area of the largest rectangle in Q1, quadrant 1, that can be inscribed under the line y equals 12 minus 3x. So let's draw the line. Y equals 12 minus 3x has a y-intercept of 12. Right? If you set x equal to 0, you get y equal to 12. Has an x-intercept of 4, because if you set y equal to 0, you end up getting 3x equal to 12. You get x equal to 12 divided by 3, which is 4. And then we're trying to inscribe a rectangle under this line, meaning it's going to be something like this. Right? It's going to touch the line there because we want to get as much area as possible. And we're trying to find what the biggest or the most area a rectangle can have under this line like that. Then again, it has to be in quadrant 1, so we can't have it go over here. All right, so I don't know what this point is here, so I'm just going to give it a name. I'm going to call it x comma y. And I know that if this is x, it means we've gone over x, and this is y, we've gone up y. So our area is equal to x times y. That's what we're trying to maximize. And in this case, our constraint is the fact that this point is on the line. So we're trying to maximize area equal to x times y. Our constraint is the fact that y is equal to 12 minus 3x. And just like in the previous two problems, we're going to take that constraint and plug it in for y up there. So we're going to say now we want to maximize the area as a function of x. Instead of being x times y, it's going to be x times 12 minus 3x. Again, it's still really just x times y. So then we're going to multiply it out. Area is going to be 12x minus 3x squared. You don't have to rewrite it as the highest power first. I just like to. So negative 3x squared plus 12x. Our vx coordinate is going to be negative 12 over 2 times negative 3, which is negative 12 over negative 6, which is positive 2. And then the y coordinate, so if I plug 2 back into this, the y coordinate is going to be 12 minus 3 times 2, which is 12 minus 6, which is 6. So the point on the curve, on the line, is going to be the point 2 comma 6. So that's the point where the area is going to get maximized. And so I think I answered the wrong question though, because it didn't ask for the point, it asked for the area of the largest rectangle. So I know then that my x is 2 and y is 6, and the area is x times y. So the area is going to be 2 times 6, which is 12. And they didn't give us units, so I just say 12. Oops, sorry. Alternatively, if I hadn't found that y was equal to 6, I could have just plugged in the 2 for x right back here and said, oh yeah, look, if I plug in 2 here, area when x is 2 is going to be 2 times 12 minus 3 times 2, which is 2 times 12 minus 6, which is 2 times 6, which is 12. So either way you do it, you still should get the same value for area. All right, so those are just a few examples of optimization problems where you have to use a constraint and a thing you're trying to maximize or minimize. I know we didn't do any minimization examples, sorry about that. But they're really the same idea. Just your parabola opens upwards instead of opening downwards. And then you find the vertex of your parabola and either find the dimensions, which are the x coordinate of your parabola, and plugging that back into your constraint to find the other coordinate, or you find the maximum area by taking your x coordinate and plugging it back into the function to find the y coordinate of your parabola, which I'm going to write as VA, not VY, which would have been exactly 2 times 12 minus 3 times 2, which is still 12. So just make sure you're answering the right question. All right, that's all I got. See you all on Monday.